The most terrifying sentence in all of physics is not the bomb works. It is not the black hole evaporates. It is this: according to our best understanding of the early universe, none of this should be here. Not the stars, not the planets, not the air you are breathing right now as you sit in that seat trying to decide whether I am going somewhere interesting. Not the seat, not you. According to everything we know about the birth of the universe, matter and antimatter were created in exactly equal proportions, and they annihilated each other completely, and the universe that was left over was empty. Perfectly, absolutely, completely empty. Nothing. Forever. And yet here we are. That is not a rhetorical flourish. That is a genuine scientific crisis that nobody has fully solved, and I want to take you through it today. Not just the problem, but the wild, strange, beautiful machinery underneath it. Because on the way to answering why something exists instead of nothing, we are going to discover some things about the nature of reality that I find almost unbearable in how strange they are. Good strange. The kind of strange that makes you feel lucky to be a conscious being in a universe that bothered to produce conscious beings at all. Let me start with something ordinary. You have a glass of water sitting on a table. You have it because somebody filled it. The water was already somewhere. It came from a tap. The tap is connected to a pipe. The pipe goes back to a reservoir. The reservoir filled with rain. The rain came from ocean evaporation. The ocean was there before the rain. There was a chain. Something came from something else. This is how we think about everything in everyday life. There is always a chain, always a prior cause, always something that existed before the thing we are looking at. It never occurs to us to ask why there is anything in the chain at all, because we assume the chain always extends backward. Someone always filled the glass. Now push that logic all the way back. Past the Earth forming from a disk of gas and dust around the young Sunday, past the sun condensing from a giant molecular cloud, past the galaxy assembling from the wreckage of earlier, smaller galaxies, past all of that. Go back 13.8 billion years to what we call the Big Bang, the earliest moment we have any coherent physics for. What filled the glass then? What came before? The honest answer is that we do not know with certainty, and I will come back to that. But what we do know, and this is the piece that should keep you up at night, is what the standard physics predicted should have happened at that moment. When the universe was born, it was unimaginably hot. Not hot the way you think of hot. Hot the way every particle was slamming into every other particle so violently that the collision energy was enough to spontaneously create new particles. You have probably heard that matter and energy are interchangeable. Einstein's famous equation tells you that. Well, in the first fraction of a second, the universe was nothing but raw energy, and out of that energy, particles were being born. And here is the key thing. Every time a particle is created out of pure energy, its antimatter partner is also created. Every single time. This is not a preference or a statistical tendency. This is a law. It is called charge conjugation symmetry, and it says that the laws of physics must treat matter and antimatter identically. For every electron born, a positron is born. For every proton, an antiproton. They come in pairs, always, without exception. And when a particle meets its antiparticle partner, they annihilate. They turn back into pure energy, 2 photons of light, and nothing else. The matter is gone. The antimatter is gone. Only light remains. So if the universe started with equal amounts of matter and antimatter, and they annihilated each other with perfect efficiency, you know what the universe should contain right now? Photons. An enormous, ancient, featureless sea of photons, traveling through a completely empty universe with no matter of any kind forever. No stars, no planets, no people asking questions, no questions. That is what the math says should have happened. And now I want you to feel the true weight of the fact that this lecture is happening. Look at your hands. Those hands are made of atoms, carbon, oxygen, hydrogen, nitrogen, trace amounts of other things. Those atoms did not come from nothing. They came from stars that lived and died before the sun was born. Those stars were made from hydrogen and helium left over from the Big Bang. That hydrogen and helium, that ordinary matter, the building block of everything, had absolutely no right to be there. It should have been annihilated. It was not. We exist because of a tiny, tiny imbalance. The best current measurement suggests that for every billion pairs of particles and antiparticles created in the early universe, there was one extra particle. Just one. All the antiparticles annihilated all the matter except that single leftover, and that 1 in a billion survivor multiplied across the entire volume of the observable universe is every star, every galaxy, every planet, every ocean, every cell in your body. You are the residue. You are the rounding error. You are the one grain of rice that was accidentally left in the pot after the cook thought he had counted them all out. Now here is where it gets strange. We did not know this was a problem for a very long time. We knew matter and antimatter existed. Carl Anderson discovered the positron in 1932 using a cloud chamber in Caltech. He was not even looking for it. He was studying cosmic rays, and he saw a track that curved the wrong way in a magnetic field. The wrong way. A particle with the mass of an electron but the charge of a proton. He sat with that result for months before he published it because he was sure he had made a mistake. The equipment was probably wrong, the calculation was probably wrong. He was a young man, and the physics establishment was full of people who would not be kind about mistakes. But the result kept coming out the same way. He had found antimatter. Paul Dirac had actually predicted it mathematically a few years earlier as a solution to his relativistic equation for the electron, but even Dirac was not sure what to make of his own prediction. He first thought the antiparticle might be the proton. The universe has this habit of being stranger than even the people who are thinking the strangest thoughts can quite handle. So we knew about antimatter, and we knew about the Big Bang by the 1960s, and we knew about the symmetry between matter and antimatter. But the contradiction, the devastating, screaming, logical contradiction at the heart of our existence only really became sharp in 1967 when the Soviet physicist Andrei Sakharov sat down and wrote out exactly what conditions would be required for the universe to produce a matter-antimatter asymmetry at all. He was not trying to explain it. He was trying to identify what the requirements were. He produced 3 conditions. They are now called the Sakharov conditions. And one of them was what physicists call CP violation, which means the universe must treat matter and antimatter slightly differently. The laws of physics themselves must be slightly biased. I want to stay with that for a moment because it is one of the most extraordinary claims in all of science. We built our entire theoretical framework, what we call the standard model of particle physics, on the assumption of certain symmetries. One of those symmetries is the combined symmetry of charge conjugation and spatial reflection, called CP symmetry. It says that if you swap every particle for its antiparticle and you look at the result in a mirror, the physics should look the same. It is a beautiful idea. It feels like it should be true. It has the ring of mathematical inevitability that physicists love, the feeling of something that could not possibly be otherwise. It is wrong. In 1964, James Cronin and Val Fitch were studying the decays of particles called kaons, strange little things made of a quark and an antiquark, and they found that the kaons decayed in a way that violated CP symmetry. Matter and antimatter behaved slightly differently. Not much. The violation was tiny, less than 1%. But it was there, unambiguous, repeated, confirmed. Cronin and Fitch won the Nobel Prize for it in 1980. And the physics world quietly had what I can only describe as a slow-motion philosophical crisis, because if CP symmetry is violated, then the universe is not indifferent between matter and antimatter. The universe has a preference. The universe chose us. But here is the problem, and this is the thing that should make you bite your knuckle with the sheer delicious frustration of it. The CP violation we measured in kaons and later confirmed in B mesons and seen in other systems is too small. Not small in an abstract sense, small in a quantitative sense. The amount of CP violation we can actually measure in particle physics experiments is not nearly large enough to account for the 1 in a billion excess of matter over antimatter that produced everything we see. We can confirm that the universe treats matter and antimatter differently. We cannot explain why the difference is as large as it is. There is a gap between the asymmetry we can measure and the asymmetry we need, and that gap is one of the most active and unresolved areas in all of fundamental physics right now. So we have gone from the question of why anything exists and we have discovered that the answer requires the universe to break one of its own symmetries, and we have confirmed that this symmetry is indeed broken. And we have found that the breakage is the right kind but not the right size, and we have no idea what provides the rest. That is the state of the art. That is where the knowledge ends and the beautiful darkness begins. Let me give you a thought experiment. Imagine you are standing in a room, and in this room there is a light switch on the left wall and an identical light switch on the right wall. The room is perfectly symmetric. You flip the left switch and the light comes on. Your friend flips the right switch and the light stays off, and the room is otherwise absolutely identical in every way you can measure. You would assume there is something different about those switches, some hidden wire, some connection you have not found. Maybe you need to look deeper. Maybe at a smaller scale, some difference will appear that explains the asymmetry of outcomes. That is the CP violation problem. The macroscopic universe is wildly asymmetric all matter, no antimatter, and the deep microscopic structure contains some asymmetry, but not enough of one. There must be something else, some deeper wire we have not yet found. Some physicists think the answer lies in a particle that has never been detected, the heavy neutral lepton, or right-handed neutrino, in a mechanism called leptogenesis. The idea is that early in the universe, some heavy exotic particles decayed in a CP-violating way that created an asymmetry in leptons, which are particles like electrons and neutrinos. That asymmetry was then transferred to baryons, protons, and neutrons through a process that happens at very high temperatures. The math of this is beautiful. The experimental evidence is so far non-existent. This is what makes it exciting. It is a real hypothesis with real predictions about things we have not yet built accelerators powerful enough to test. Others think the answer involves supersymmetry, a theoretical framework that proposes every known particle has a heavier partner particle, which provides new sources of CP violation beyond what the standard model contains. Supersymmetry has been looked for extensively at the Large Hadron Collider at CERN. So far, it has not been found. This does not mean it is wrong. It means nature, if it is supersymmetric, chose parameters that have put the supersymmetric particles just out of reach of our current machines. Or it means supersymmetry is not the answer. We do not know which. The machine keeps running. The search continues. Now let me do something that I love to do, which is zoom out far enough that the specific problem we have been discussing becomes a window into something much larger and stranger. The question of why matter exists is really a special case of a question that has no obvious scientific answer at all, which is, why does anything exist rather than nothing? Not why does matter dominate over antimatter? That is a physics question with a physics answer, even if we do not have the complete answer yet. But the deeper question, why is there a universe at all? Why is there something rather than nothing? This question is usually assigned to philosophy or theology, and I understand why, but I want to resist that assignment for a moment, because physics has something genuinely interesting to say about it, even if physics cannot fully resolve it. The first thing physics says is that nothing is not what you think it is. When most people imagine nothing, they imagine an absence, a dark, empty box. No particles, no fields, no energy, no space, no time, just nothing. But quantum mechanics tells us that even the lowest energy state of a quantum system is not zero. It cannot be zero. There is a result in quantum mechanics called the Heisenberg uncertainty principle, and one of its implications is that you cannot have a perfectly defined energy of zero, because knowing the energy precisely would require knowing it at a perfectly defined moment of time, and these two quantities cannot both be precisely known simultaneously. What this means physically is that even in what we would call empty vacuum, the emptiest empty there is a restless, perpetual, irreducible fluctuation of energy. Virtual particles are constantly popping in and out of existence. Fields are constantly vibrating at their lowest allowed modes. The vacuum is not empty. The vacuum is full of activity. This is not speculation. This is measured. The Casimir effect, which is a measurable force between two parallel metal plates placed very close together in a vacuum, is a direct experimental confirmation that the vacuum has energy. The plates are pushed together by the difference in vacuum fluctuation modes between the space inside and outside them. The vacuum is doing something. The vacuum is never truly nothing. So in a technical sense, the question, why is there something rather than nothing, may be malformed. There may not be a nothing available. The laws of quantum mechanics may not permit the vacuum to be empty in the way we imagine nothing to be. What we call nothing may already contain the seeds of something. But this is not fully satisfying, and I want to be honest about why. Even if the quantum vacuum cannot be empty, we still have to ask why there is a quantum vacuum. Why are there laws of physics at all? Why is there a universe that obeys mathematical rules, rather than a universe that is random and chaotic in a way that produces no structure whatsoever, or no universe at all? This is the question that sits at the very bottom, where physics meets something it cannot fully address on its own, and I think it is important to be honest about where that boundary is. Eugene Wigner, one of the great physicists of the 20th century, wrote a famous paper in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He was pointing at something deeply strange. The mathematics we invent for purely abstract reasons, reasons of internal mathematical beauty and consistency, with no particular physical application in mind, turns out, over and over again, to be exactly the mathematics that describes the physical world. The complex numbers, invented centuries before anyone needed them for physics, turn out to be the natural language of quantum mechanics. Non-Euclidean geometry, developed by Riemann purely as an abstract mathematical exercise, turned out to be exactly what Einstein needed to describe the curvature of space-time. Lie groups, which mathematicians developed for purely algebraic reasons, turn out to describe the symmetries of particle physics with uncanny precision. Why? Why should the universe care about what mathematicians find beautiful? Why should the abstract and the physical converge so completely? I do not know the answer to this. Nobody does. But I find the question one of the most exciting things I have ever encountered, because it suggests that there is something deep about the relationship between structure and existence, that the universe is not just some arbitrary collection of stuff, but something that is fundamentally mathematical in its bones, in a way we do not fully understand. Now I want to bring this back to the matter-antimatter problem, because there is a perspective from which the question is not why there is a small asymmetry between matter and antimatter, but rather why the asymmetry is not much larger. Think about it the other way. The standard model of particle physics, which is our best theory of the fundamental particles and forces, actually predicts a CP violating effect that comes from the structure of the strong nuclear force, the force that holds quarks together inside protons and neutrons. The parameter that controls this effect is called theta, and the standard model places no constraint on its value. It could be anywhere between 0 and a very large number. The amount of CP violation associated with this parameter could be enormous. But when we measure it, we find that theta is essentially 0, not exactly 0, we cannot measure it exactly, but extraordinarily small, much smaller than there is any obvious reason for it to be. This is called the strong CP problem, and it is one of the deepest unsolved puzzles in physics. Why does a parameter that could be almost anything turn out to be almost nothing? One proposed solution is a new particle called the axion, predicted independently by Roberto Peccei, Helen Quinn, Frank Wilczek, and Steven Weinberg in the late 1970s, which would naturally drive the theta parameter towards 0 through a clever symmetry mechanism. The axion has never been detected either. But it is a beautiful idea, and there are experiments running right now, tunneling slowly through the parameter space where the axion might live, listening for a signal. In a very literal sense, right now, as you sit here, someone is searching for the particle that might explain why the strong force respects the symmetry it has no apparent reason to respect. Here is the thought experiment I want to leave you with before I bring this all together. Imagine that somewhere in the universe, very far away, too far to ever communicate with us, but real there is a galaxy made entirely of antimatter, anti-hydrogen stars, anti-carbon planets, And on one of those planets, there is an anti-being made of antimatter who is as curious as you are, and who has worked out the same equations you have, and who has asked the same question. Why does matter meaning, from their perspective, antimatter dominate over antimatter meaning, from their perspective, matter? And they have found the same asymmetry in their kaon decays, the same CP violation, the same gap between the measured asymmetry and the required asymmetry. From where they stand, the universe chose them. From where you stand, the universe chose you. The truth is that the universe, in its very first moments, performed a kind of election. The candidates were matter and antimatter. They were functionally identical. The election was almost perfectly tied. And out of some tiny bias, some asymmetry in the laws of nature that we have not yet fully characterized, matter won by 1 vote in a billion. And the winner did not just win, the winner took everything. The loser was annihilated, converted to light, dispersed. And the light still fills the universe. It is the cosmic microwave background radiation, the faint afterglow of the annihilation, observable today in every direction, the evidence of the great destruction that had to happen before anything we recognize as the universe could begin. When you look at a microwave image of the cosmic background radiation that mottled ancient light from 380,000 years after the Big Bang, you are not looking at the birth of the universe. You are looking at the aftermath of the massacre. You are looking at what was left over after almost everything was destroyed. The slight variations in temperature that you see in that image, those are the seeds of all future structure. The slight overdensities in the matter that survived, the whispers of the galaxies and stars and planets and you that were to come. All of that structure grew from the single particle out of a billion that had no right to survive. I find this almost paralyzing in how beautiful it is. The universe is full of things we find magnificent. The spiral arms of galaxies, the iridescence of a butterfly wing, the structure of a protein, the beat of a heart. And every single one of those things exists because of an accident, because of a statistical hiccup in the first trillionths of a second, because the universe had a bias it had no reason to have. You ask why the universe exists, the physicist will tell you that the most honest answer is it almost did not. There was a very real sense in which the universe almost succeeded in erasing itself. The matter and the antimatter tried to cancel each other out, and they very nearly did. What you call the universe is not the original universe. It is the leftovers of an almost complete erasure. There is something here that I think goes beyond physics, not into religion or mysticism, but into a kind of awe that is available to anyone who is willing to look at the numbers clearly. We are made of the survivors. We are the descendants of the tiny fraction that the annihilation could not touch. Every atom in your body is here because of a fluctuation in the laws of nature so small that it is almost below the threshold of detection, a 1 part in a billion preference that was just enough, just barely enough. And now those survivors, those accidental atoms, those rounding errors of the early universe have assembled themselves over 13.8 billion years into a configuration complex enough to be curious about where they came from. That is the thing I cannot get over. Matter became conscious. The accident became aware of itself. The residue of the annihilation started asking questions about the annihilation. We do not know exactly why the universe has a matter-antimatter asymmetry of the size it has. We do not know whether leptogenesis is the mechanism or whether something else is. We do not know whether the axion exists. We do not know what new physics beyond the standard model is lurking at the energy scales we have not yet been able to probe. These are not failures. These are open doors. These are the questions that will define the next generation of physics, the experiments that will run in my colleagues' lifetimes, the ideas that have not yet been thought. But I want to tell you what I think the deepest lesson is. And this is the part where I stop giving you answers and give you something better. Every theory we have ever had about the fundamental nature of reality has at some point contained a hidden assumption about symmetry, about what the universe treats as equivalent. And every time we have been willing to look carefully enough, we have found that the symmetry we assumed was broken. Space is not symmetric under exchange of matter and antimatter. The vacuum is not symmetric under rotation spontaneous symmetry. Breaking is at the heart of how particles acquire mass through the Higgs mechanism. Even time might not be fully symmetric. The laws of physics look almost but not quite the same, running forward and backward. Every time we find a broken symmetry, we find a new structure that the symmetry was hiding. Every asymmetry is a clue. Every imperfection in the mirror is pointing at something real. So when you ask why the universe exists instead of nothing, perhaps you are really asking why the universe is imperfect, why it has asymmetries, why it did not cancel itself out. And the answer might be that a perfectly symmetric universe is, in a deep sense, not a universe at all. Perfect symmetry is the same as nothing. Nothing is perfectly symmetric. It treats all possibilities as equal, which is another way of saying it has no structure, no content, no story. What we call existence might be nothing more and nothing less than a broken symmetry. The universe exists because it is unequal. It exists because something, somewhere, in the first instant, was slightly more than something else. You are a broken symmetry. You are what happens when the universe fails to cancel itself out. You are the imperfection in the mirror. And if that does not give you pause, if you can sit with that and feel nothing shift in the way you understand your own existence, then I envy you your composure, because I have never managed it.